recording. Okay. So, Rama, thank you.
You're
So,
welcome.
the moment the car starts, whilst the car moves forward, human beings will be lurking in our seats. Okay. You adjust yourself to the new car's velocity by the seat. When the seat pushes, the upholstery of the car seat pushes you to adjust yourself, then you then be moving with the car's velocity. So, initially, you will be opposing a change in your velocity. In the same way, when the car is going and there is a sudden stop, the moment the brake is applied, application of the brake, okay, resists the motion, thereby reducing the velocity. But you will still be moving forward for a while. So you move forward for a while before you adjust your body to the change in the new velocity. Please, I'm sure you have all experienced this before. Have you?
Yes, please.
Yes. So this is how we oppose our own inertia. That is why if you are in a moving bus and you don't have your hand gripped to that thing, that string which is suspended within on the rope or on a bar, and there's a sudden break, you'll be moving forward in the bus. Okay. Now, so if you're in a car and there is an unfortunate incident where your car hits another car or another car hits yours, or it veers off from the road and then hits, a bridge or cover somewhere, what happens is that the moment, let's take a situation where your car hits another, your car hitting another car would have a situation where your car's velocity is reduced because there is an opposing force. Okay. And this situation will quickly change the velocity of the car. But as human beings, we are always opposing a change in our velocity. So when that unexpected situation happens and it hits yours, you move in the opposite direction. Okay. Because you want to resist a change in your velocity. Now, your acceleration in the opposite direction depends on the magnitude of the force which unfortunately strikes yours. Okay, so usually when most accidents which occur on our road, the fatalities involved are due to the non-usage of the seatbelt. Okay, when during a collision, you would oppose a change in velocity by moving in the opposite direction. Okay, and the acceleration with which the passenger would move depends on the magnitude of the force which hits the external force which hits yours. So whilst, okay, the person accelerating for, if you have the seatbelt on, it can easily grip you into your seat. And this will prevent a situation of the person being thrown out of the windscreen or hitting the dash bar of the vehicle. This is how the seatbelt prevents or is applied in Newton's first laws of motion. Please, are you okay? Are we okay?
Yes, please.
Okay, so because we have an inherent um opposition to a change in velocity. That is why it is also not advisable to stand on top of a bus, because when you are on top and there's a sudden break or something happens, you will still be accelerating forward, and there's no seatbelt to hold you. So this is how the first law is applied. Then the second law, application of the second law goes to any accelerating body. It is applied to any accelerating body. For an acceleration to occur, there must be external force. So every accelerating body must have an external force causing the acceleration. And so Newton's second law applies to any accelerating body. So long as there is an acceleration, there will be an external force which is causing the acceleration. So this applies to accelerating body. So once there is an external, when there is an acceleration, there is an external force responsible for the acceleration. Okay. Then the third law, application of the third law goes with one, launching of rockets. How rocket is launched in space. Apply the third law. How a rocket is launched in space. Apply the third law. Then two, this firecrackers, applied in firecrackers. We are in Xmas period. These firecrackers that are actually used in our communities works on the principle of the third law. These two, okay, in the case of the rockets, in the rocket, there is a burning fuel within the tank. So the burning fuel, okay, when the fuel is burned, the exhaust, the exhaust fume is made to leave through the nozzles. And as the exhaust fume leaves without force, there is a reversal force exerted on the rocket. And that is what propels the rocket up in a vertically upward motion. So long as that burning occurs within the tank, and then the exhaust fume is made to escape through the nozzle, there will be a reversal reactional force acting on and that is the principle on which the rocket and then the firecrackers also work. Now, a basic demonstration of this is also the kind that when you inflate a balloon, okay, and then you allow the gas within to escape through the balloon opening, there will be a reversal movement of the balloon. And that is the principle on which these two also works. Then the third application is the recoil velocity of the gun. Recoil velocity of the gun. You see, if you are an amateur and then you are made to fire a gun, the tendency that you can misfire and then shoot a wrong target is very high. The reason is that whilst you fire and then the bullet, okay, moves out of the nozzle, there is the escaping of the bullet with that force exerts a reversal force on the gun. So if you are not somebody who is a professional in handling it, when you shoot, your hand will shake because of that reverse force or reverse velocity on you. So the moment you shake, meanwhile, when you are shooting, you have to target. But the moment there's that reversal force on you and it shakes your hand, it can change the direction and you can easily misfire. Those of you who have watched war films before, look at the armored vehicle. Whenever the armored vehicle shoots, it shakes the armored vehicle and the ground as well. That is the recoil velocity or force when the bullet is escaping. So these are some of the applications of the third law. Please, if you have any question, quickly ask and let's zoom into calculation. If you have any question to ask concerning what you've said so far, bring it up. You can also read and add on, okay, with the applications of Newton's third law of motion. All right. Once you are not saying anything, let's move on to see how we can apply this in calculation or in solving problems. Okay, question 1. Wait, give me a second, I'm coming. All right, I'm taking shots of some questions and then drop it on the platform. Okay, so the question is dropped on the platform. Have you seen it? Please, have you received it? Hello? Yeah, Benko, are you there?
Yes, please.
Okay, one of the question goes like this. A body is at rest under the action of the forces shown in the diagram. Fill in the value of A. A body is at rest under the action of the forces shown in the diagram. Fill in the value of A. Okay, so let me give a quick sketch. We have this body.
Mr. Abia, please, the question haven't come.
Really?
Yes, please.
Does it come?
Yes, please.
So the first one, a body is at rest under the action of the forces shown in the diagram. Fill in the value of A. So we have A, then we have 45 Newton force, and then 86 Newton. We have to find the value of A. But the earlier information given is that the body is at rest, okay, under the action of the forces. And once the body is at rest, it means we have a state of static equilibrium. In static equilibrium, the net forces acting on the body is equal to 0, and the body is stationary. So once the body is stationary, it means the net force acting on it is equal to 0. So all the forces in one direction must balance the forces in the opposite direction. So A plus 45 must be equal to 86. Therefore, A is equal to 86 minus 45, which is equal to 4.1 Newton. So the value of A will be equal to 41 Newton. This is a typical question under static equilibrium. Let's look at question 2. The second question also says that a body moves horizontally at a constant 4 meters per second velocity. So this is a constant velocity. A body moves horizontally at a constant velocity of 4 meters per second under the action of the forces shown. Okay, find X. So this is a quick sketch. We have 500 Newton force here, 500 Newton force at the other end, then X Newton up, and downwardly we have 1240 Newton force and 450 Newton force. Help me find the value of X. These are fundamental questions, but let me see how you can determine the value of X.
You add 450 and 1240.
Now, what do we do with the velocity given? What do we do with the velocity given? Yes, I want views. Adwa, what do we do with the velocity? We're given a velocity of 4 meters, constant velocity of 4 meters per second. So what do we do with it? Adwa?
Yes, please.
Eh,
It's a constant velocity.
so,
That means the net force swapped up to 0, so you don't use it.
okay, that is Adwa's view. Any other view? What do we do with the constant velocity of 4 meters per second? Yaba, answer. Give me what you think. Okay, now, you see, here too we have dynamic equilibrium. And what is dynamic equilibrium? Equilibrium state obtained by a body when the net force acting on the body is equal to 0 and the body moves with a constant velocity. So once we are given a constant velocity of 4 meters per second, okay, then it means this is a dynamic equilibrium state of a question where the body has a net force of 0 acting on it, yet it moves with a certain constant velocity value. So the constant velocity tells us that this is a dynamic equilibrium kind of question. And we expect the total forces acting in all directions on the mass to be equal to 0. So let's then look at it. Okay, so this side is equal to this side horizontally. 500 balances this. And so the sum of these two forces here must also be balanced by x. So x is equal to 1240 plus 450, which is giving us 1690 Newton. Plus, are we okay? Are we fine? Hello, are you okay?
Yes, sir.
So the constant velocity is to tell us that this is a dynamic equilibrium kind of question. I've sent another one to you. Help me determine the value of x and y. I sent another question onto the platform. Help me find the value of x and y.
Be equal to 100. And since it has a constant velocity, it means it will not be needed in the answer of the question. So you get x is equal to 120 Newton minus 66 Newton, giving you 54 Newton.
Okay, so we have a dynamic, the constant velocity simply tells us that the question is about dynamic equilibrium. So let's see, confirm, so that we could confirm whatever you got. So once we have that, then the total forces 120 Newton must balance x plus 66 Newton. Therefore, x is equal to 120 minus 66. What is 120 minus 66?
50.
50 what?
4.
Okay, so 5, 4. 5, 4 Newton for x. Then the y. 55 plus y must be equal to 75 plus 42. Therefore, y is equal to 62 Newton. So that must be it for x and y. Now, I sent another question. Check. I sent another question. A body of mass 20 kilogram. A body of mass 20 kilogram is being pulled along the floor with constant velocity by a horizontal force by a horizontal force of magnitude 140 Newton. Find the normal reaction acting on the box and mu, the coefficient of friction between the body and the floor. So find the normal reaction acting on the box and mu, which is the coefficient of friction between the body and the floor. Start work. And Lizzie, are you there?
Yes, please.
I'll take you give us your answer. So, or you explain it to us.
I didn't understand.
So when I was explaining, Lizzie, you were not listening. Awuresi. Okay, you solve it. Let's see. We'll all discuss it afterwards. So Lizzie, next time pay attention.
Yes, please.
Everybody must try. Everybody. So once the body is being pulled with a constant velocity, then it means we have, Lizzie, are you there?
Yes, please.
So once the body is being pulled with a constant velocity, then we have a situation of dynamic equilibrium. And Lizzie, what is dynamic equilibrium? Lizzie, what is dynamic equilibrium? You are not listening. You are not. Charlotte, what is dynamic equilibrium?
Constant velocity.
So, where, Charlotte, you should talk about the other one too. Where a body, okay, moves with a constant velocity, whilst the net force acting on the body is equal to 0. So the net force acting on the body is 0, yet the body moves with a constant velocity. So this constant velocity tells us that we have a static, dynamic kind of equilibrium. So let's put the information down into a kind of diagram. There's the floor, there's the mass, okay, 20 kilograms. The mass is 20 kg. Now, it is being pulled along the floor with a constant velocity by a horizontal force. So this horizontal force pulls it. And the magnitude of the horizontal force is 140 Newton. Now find the reactional force acting on it. Okay. Now, once it has a weight, it will certainly have it has a mass, it will certainly have some weight. So the weight W is equal to mg. The body lies on the horizontal floor. Once it lies on the horizontal floor, then it means its reaction would be opposite to the weight. Reactional force is always perpendicular to the surface. Now, you see, what is reactional force? A reactional force is a force which always presses two bodies put on each other together. It's a force which would always press two bodies together tightly. Now, this force which always presses the two body is always perpendicular to the surface. That's why we call it as the normal reaction. Normal reaction. It is termed as normal because this force is always perpendicular to the surface of contact. Okay. And I've told you its function. Now, when the body lies flat on the surface of another, the reactional force is simply equal to the weight. So R is equal to weight, which is equal to mg. Therefore, the reactional force is equal to 20/10. And R is equal to 200 Newton. How many of you got 200 Newton for the reaction? Show by hands if you had 200 Newton for the reaction. Nobody got that. Ajua had it. Okay, so please. All right. When the body...
Dear,
Hello.
please, the reaction, I don't get it in the normal reaction.
The normal reaction is the reactional force. Its name is actually this, normal reaction. But sometimes we don't add the normal to it and call it a reaction. Okay. But it is normal because this force which presses the two bodies together is always perpendicular to the surface. That's why we sometimes add the name normal. Are you okay? So the reaction is always perpendicular to the surface. Charlotte, are you okay? All right. So the next question demands that we find the coefficient of friction. The coefficient of friction. Now, once the body is under dynamic equilibrium, then the net force acting on the body in all directions must be 0. So the reaction R is balanced by the weight. This must be... Hello?
Please, the network was so I didn't hear anything you said.
What I'm saying is that the normal reaction is the same as the reaction. We sometimes add the adjective normal because the reaction is perpendicular to the surface. It's perpendicular to the surface. So the normal simply means that perpendicular. Okay.
Yes, please.
But the normal reaction is the same as the reaction. Okay, so if we have dynamic equilibrium, then this is equal to this, and this must be equal to the force at the other end. Okay. But once the question talks about calculate the coefficient of static friction, then it means that there is an opposing force at the other end. There is an opposing force.
Please raise your camera up.
There is an opposing force at the other end. And frictional force opposes motion. So once the net force acting on the body is equal to 0, then 140 Newton must be balanced by the frictional force. And frictional force F is given by coefficient of static friction times the reaction R. Therefore, when we equate 140 Newton to mu R, we can find mu, which is the coefficient of static friction. R is equal to what we have found, 200. Therefore, mu is 140 divided by reaction, which is 200. This and this will cancel. And so what is 14 divided by 20? What we have?
0.7.
Okay, so this is 2 times 7 over 2 times 10. So this is 0.7. And that's the coefficient of friction. Any question? Any question?
No.
All right. Okay. Let's put another question on calculation on the first law down. One end of a light inextensible string. Okay, let me take a shot and send it to the group. Okay, so I've sent it. And the question goes like, okay, it hasn't come, it hasn't been submitted, so. All right, so it is submitted. One end of a light inextensible string. One end of a light inextensible string is attached to a horizontal ceiling, and a particle of 4 kg is attached to the other end of the string, and a particle of 4 kg is attached to the other end of the string. The particle is pulled sideways by a horizontal force of 20 Newton until the equilibrium position is reached. So it is pulled sideways by a horizontal force of 20 Newton until the equilibrium position is reached. Find the tension in the string, capital T. We have to find the tension in the string, capital T, and the angle theta which the string makes with the vertical, into bracket, in equilibrium. So let's take the question one after the other and then draw. Let's take it one after the other and draw. One end of a light inextensible string, meaning the string is light and cannot be stretched, extended. You can't stretch it. So one end is attached to a horizontal ceiling. So let's assume the ceiling to be this. So this is the string. One end is attached to the horizontal ceiling. So this is one end which is attached, and the other end has a mass connected to it. And a particle of mass 4 kg is attached to the other end. So this is the mass 4 kg. If the mass is 4 kg, you can find the weight. Now, the particle is pulled sideways by a horizontal force of 20 Newton. So this particle is pulled by a horizontal force. It is pulled to one side by a force which is horizontal, and the magnitude of this force is 20 Newton. Now, practically, this is what the question is talking about. Assuming this is the mass, my hand is the ceiling. Initially, it is like this. Now, when I apply a horizontal force and then push it sideways, this is how it will behave until equilibrium, where the total forces around the mass cancels out. So when it is, the moment is like this, and there is a force pulling it horizontally through one side. Now the string would bend at an angle to the horizontal, to the vertical. So the mass, which was initially like this, now will look like this. Okay, so the string will now make a certain angle theta with the vertical. This is the horizontal force pulling it. Then once it has a mass, its weight would act in this direction. And the weight will be 20, the mass is 2. So 20 Newton. Now, because this is a string, the string always has a tension. The tension is always directed to where the support is. So this is the horizontal ceiling supporting the whole arrangement. And the tension will be directed to where the support is, T. Now, the question is that we are to find the angle and then the tension within the string. Please, are you okay with the drawing, class? Are we okay? Hello, are you okay? Hey, today your silence is becoming a ailment. If you are okay for us to move on, give me feedback. If you are not, you draw my attention so I explain. But nobody seems to be talking on the platform. What's the problem? Are we okay with the diagram?
No, please.
This is what I was requiring. Please give me feedback when I ask a question. Online class isn't about the teacher alone doing the talking. Give me feedback. When I ask, do so. This is supported. This is the ceiling, a horizontal ceiling. Okay. One end of the string. So this is the whole string. It's supported to the ceiling. One end is also connected to a mass of 2 kilograms. Okay. Then you are told that a horizontal force of 20 Newton pulls this mass sideways horizontally. So there's a force pulling this. Yaba, mute yourself. So there is a horizontal force pulling this. Now, initially, this is how the whole thing is. If there is a horizontal force pulling it, pulling the mass, the string will be tilted at an angle theta. Okay. And so before, there's no angle between this and the string. Now there will be an angle. So that's what I've illustrated. But this is the horizontal force pulling it. This is the weight of the mass. Now, the tension in the mass is always directed to where there is support. This whole arrangement is supported at the ceiling. So the tension will be directed to where the ceiling is, because that is the support. This is an imaginary vertical. Okay. And so that is the how the drawing or how the whole arrangement will be when the horizontal force of 20 Newton acts on it. Now the question is that we have to find the angle of tilt and then the tension T within the string. Adwa, are you okay with the explanation? Adwa, go ahead.
Mr. Please, the weight, won't it be 40 Newton?
I took the mass to be 2. So okay, so if it's 4, then the weight will be 40 Newton. Thank you. Okay, so now the bone of contention is how to, you see, we are told that it is pulled until equilibrium position. Equilibrium position is obtained. Now, at equilibrium position, it means that the total forces acting on the mass in all directions must sum up to 0. So, once this is the weight vector, there will be another vector in the opposite direction. Once this is the force, horizontal force pulling it, there will be another force in the opposite direction. And this would be balanced by this. This would also be balanced by this, so that this is in equilibrium. At equilibrium, the net force acting on the mass is 0. Okay, so what it means is that we need to resolve this tension acting at an angle into its vertical and horizontal component. You've done vectors. So what do you think will be the horizontal component of this tension here? What will be this component? Yes. What will be the horizontal component of the tension here? Yes. You have this. You have the tension is here. So what will be this component?
T cos angle.
So this will be T cos of theta. And then this component would also be T sine theta. Okay. Now, under equilibrium position, as I said, now look at this. Because of equal vectors, this component will be equal to this component. So if this is T cos theta, this will also be T cos theta. Equal vectors. Vectors are equal whenever they have the same magnitude, direction, and are parallel to each other. So we realize that the T cos theta will be balanced by 40 Newton. Then the T sine theta would also be balanced by 20 Newton. So we have equation 1, we have equation 2. Now divide equation 1 by equation 2. When you divide equation 1 by equation 2, you have T sine, no, divide equation 2 by equation 1 rather. 2 by equation 1. So T sine theta over T cos theta equal to 20 over 40. And what is sine theta over cos theta? Yes, what is sine theta over cos?
Tan theta.
So that is tan theta. Therefore, tan theta is equal to 0.5. So you find the tan inverse of this. Theta is equal to the tan inverse of 0.5. Find that out for me. Tan inverse of 0.5.
$26.57.
So theta is equal to 26.57 degrees, approximately. Now, once you have theta, you can easily use any of the equations to find the tension in a string. Do that for me. We found theta, so you can easily determine the tension in a string. What did we get for? What did we get for the tension?
44.74.
So the tension will be equal to 44.74.
Yes, please.
Now, if here you can use any of the equations. If you use equation 1, okay, T cos of the angle 26.57 is equal to 40. Then you make T the subject. So if you are not clear with how to do that, that's it. Or you can use this. Now, another way of determining the angle is this. And open your eyes to the diagram. I earlier told you that under equilibrium position, this component is balanced by this. So in actual fact, it also means that the T sine theta component is equal to 20. If you are equating this, so this side is 20. Then the T cos theta component is also equal to 40. So this side is in fact equal to 40 Newton. So you have a kind of right angle triangle. This is theta 40. And this is 20. So if you have a right angle triangle like this, can't you find tan when you know the opposite of the angle and then the opposite of the right angle triangle and then the adjacent of the right angle? So using tan theta, this is equal to 20 over 40, and you can also get the same results. So that's another way of determining it. Is that clear?
Yes, please.
Yes, please.
Okay. Another question. A brick of mass 6 kilograms. A brick of mass 6 kilograms rests on a sloping roof. It rests on a sloping roof inclined at 30 degrees to the horizontal. Inclined at 30 degrees to the horizontal. A frictional force F acting up the plane holds the brake at rest on the roof. A frictional force. Hey, Yaba. Yaba, mute yourself. We are getting feedback here. A frictional force F, capital F, acting up the plane holds the brake at rest on the roof. Find the frictional force F. A brake of mass 6 kg rests on a sloping roof, inclined at 30 degrees to the horizontal. A frictional force F acting up the plane holds the brake at rest on the roof. Find F, the frictional force. So this is like a brake on an inclined plane, okay, tilted at 30 degrees. Give it a try for about 3 minutes. Gravity is still
Steady.
10. Hello.
Steady.
Charlotte.
Please, can you send the picture of the question onto the group?
Okay.
Thank you.
Oh, it is done. Hello, have you found it?
Thank you. Please, I'm checking.
I mean, the rest of you. Have you found the question?
Yes.
Okay, so give it a try for about 3 minutes. Within 3 minutes, then we discuss. Hello. Okay, so I'm sure you are true. Hello.
Hi.
Can we discuss it? Are you true? But did you do inclined plane at school? Class, did you do inclined plane at school?
Yes, please, we brushed through. We didn't really learn.
And some of you didn't do it. Okay, then I think we have to look at inclined plane and then as for the inclined plane, the velocity and those things are not so key. They are just surface inclined plane. Okay, so an inclined plane is a simple machine. It's a simple machine. It is often used to load and offload goods and materials from vehicles. So this OA is the length of the plane. That's the height of the plane tilted at an angle theta. Now on an inclined plane, if this is the body on the inclined plane, the theory of an inclined plane is this. This is the weight of the body on the plane, on the inclined plane, not aeroplane. So this is the weight W or M. This is the reactional force pressing the body and then the surface of the plane together. So reactional force is always, as I said, it's always perpendicular to the surface. Okay. Now, on an inclined plane, one thing you must understand is that when an inclined plane is tilted through an angle theta, the angle between the weight, W, and then the reaction, this is an extended line of the reaction. So we will also take this to be reaction prime. This angle between the weight and the reaction is always equal to the angle of tilt. So when you tilt this by 30, this will also be 30. Whichever angle you tilt, this is okay. But let's understand let's prove it to see why this is always equal to this angle of tilt. This is the normal, the reaction. We are saying that the reaction is always perpendicular to the surface. So this angle is 90. And what do you think will be this angle? What do you think will be this angle too? Yes. If this is 90, what do you think will be this angle? Hello? Plus,
Hi.
if this is 90, what will be this angle as well?
90.
What about the angle from here to this?
90.
Good. Now, this is O, A, B, C. This is D. Let's indicate this as E. So angle OEC is equal to 90. So angle OEC, we mean this whole angle is 90. Now, if this is 90, the weight vector, the weight is always perpendicular to the horizontal or the ground. OB is the ground, and the weight is always perpendicular to the ground because of gravity. So if this is 90, what do you think will be this angle? Angle OED. What will be angle OED? OED, this small angle.
60 degrees.
Come again.
60 degrees.
Look at it. Oh, this is theta. This is 90. What do you think will be this angle?
60 degrees.
No, you can't say 60. Because this is theta. This is 90. What about this angle?
180 minus 90.
So, when this is 90, this plus this must also be 90, isn't it? This angle plus this angle must also be 90, isn't it? So, angle OED must be equal to 90 minus theta. The reason is that once this is 90, if this plus this must sum up to 90. Assuming this is 30, if theta is 30, this will be 60. If theta is 60, this will be 30. So angle OED must be equal to 90 minus theta. Now, we know that the whole of this angle is 90. So angle OED plus angle EDC. Okay, let me make it CED rather. CED is equal to 90. This is because the letter at the middle is what represents the angle. So angle CED to be this small angle. So this angle plus this angle is equal to 90. So look at something. Assuming this is A and this is X. X is this. So this is actually angle X. The angle X is angle OED. Okay. But we know that X plus what we have represented as A must be equal to 90. And that's what we have written here. So if angle X is this, then A is equal to 90 minus X, isn't it? Isn't it? A is equal to 90 minus X. And so if X is equal to 90 minus theta, then we have A given us 90 minus X, which is 90 minus theta. Therefore, when we expand, we have 90 minus 90 plus theta. This and this is 0. So we have A being equal to theta. This angle A being equal to theta. So when this angle is theta, this will also be theta on an inclined plane. Are we fine?
Yes.
So that's it with an inclined plane. On an inclined plane, if the plane tilts by theta, the angle between the reaction and this is also theta. Now, when you resolve the weight by this is, you have this component being perpendicular to the inclined plane. And this is mg cos theta when you resolve it. The perpendicular, the parallel component to the inclined plane is mg sine theta. Please, because you have done part of it, that's why I'm going through it. I'm just rushing through it. So if this is the perpendicular component, there's the parallel component. Due to equal vectors, this component can be brought on the inclined plane OA. So the parallel component, which is mg sine theta, can also be along the inclined plane. So on an inclined plane, a component of the weight mg, which is perpendicular to the plane, perpendicular to the inclined plane, we have is equal to mg cos theta. Then a component of the weight which is parallel to the inclined plane, we have is equal to mg sine theta. Mg sine theta. I'm doing this because some of you haven't treated anything on inclined plane. Anything on an inclined plane. So now, if you look at vertical and horizontal equilibrium along the plane, you can conclude that, okay, then the reactional force can be balanced by the component of the weight perpendicular to the plane. So on an inclined plane, R is equal to mg cos theta. When a body lies flat on a horizontal surface, the reaction, we saw it to be mg. We just applied it. But please, on an inclined plane, the reaction is equal to this. So note this. On an inclined plane, reaction is equal to mg cos theta. When the body is just flat on the surface or on the ground, reaction is this. Now, another observation is that you see the components of the force of the weight parallel to the plane, mg sine theta. If you look at the other end, there is no balance. So we say that the mg sine theta is unbalanced, meaning there's no force balancing it. And this explains the reason why whenever you create an inclined plane and you drop something on, it is always falling down the plane. So the result on an inclined plane, there's a resultant force which acts down the plane. So on an inclined plane, there is a resultant force mg sine theta, which always acts down the plane. A very, very important thing to understand. So this explains the reason why whenever you create an inclined plane. An inclined plane can be this. I've created what I have within my hand. Let me tilt this a bit. I've created an inclined plane. Once this is not just flat, but there's a tilt. Okay, an angle of tilt. I've created an inclined plane. And whenever you drop an object on an inclined plane, it is dropping down. It is accelerating down the plane. And this acceleration of the body on an inclined plane downwardly is always caused by the mg sine theta component. And so there is a resultant force mg sine theta component acting down the inclined plane. Please, are you okay?
Yes.
This is always there. This is always there. It's vector. It's downward the plane always. Okay. So we have just a minute to end. Okay, so it's like introducing an inclined plane. So in fact, we'll end here after your Xmas break. We'll continue. But in fact, you must turn over a new leaf whenever you come after Xmas, because the way these days you you actually act during classes. I'm not happy with it. Be responsive. Whenever there is a need for you to talk, express your views. In fact, you kill my spirit whenever you do that. Turn over a new leaf whenever we resume after Xmas. Else, I'll tell you later. Until maybe after Xmas, which is precisely, I don't know, but until after Xmas festivities. In fact, bye-bye to each one of you. Take care of yourself.
Thank you, Mr. Dear.